Hey, happy holidays. Happy President's Days, all of you. This is Celso Batalha Chotin, and today we don't have class, but I would like to give the seed of discussion that is closing next week. It's about our first article in Astro News, and I would like you guys to read that article and answer the two questions that are already available in our Canvas course, and I will give you the seeds in a little bit. As you notice, I don't have a content this week because chapter 2 is very, and 4, because I blend these two chapters, 2 and 4, they are very extensive in the sense that it helps us to, for the first time, not only visualize what is out there in the sky, but also to be able to give us some understanding on how all these the different motions we detect on an hourly basis, or if you keep track of stars every 2 weeks or so, you notice they have apparent motion in respect to our vantage point. And so we learn about daily diurnal motion, which is caused by Earth's rotation on its axis. And we also learn about Earth revolution around the sun, which causes the constellations to slowly shift westward, and we can perceive those shifts in respect to the sun. I mean, um, we perceive those shifts if we observe them at the same time every, let's say, 3 weeks or so, and then we or 2 weeks, and then we see they are not in the same spot at the same time we observed previously. So Earth revolution around the sun also causes different seasonal changes on Earth as in seasons. This is one of the main points of this chapter, is caused by Earth axis of rotation inclined being inclined with respect to the orbital plane. Okay. So what I'd like to do is to spend some time with the software that display the night sky, and I would like to open 10 minutes or so every Monday when we have our chat room and outline some of the features in the night sky, and perhaps um, we grow on it. So the moon right now, if you want to keep track of the moon's phase, which phase the moon is right now, you can go to our course, and in the first module, I have a link to current moon phase, and the moon is in a waning crescent phase. Waning crescent phase. So if the moon is in a waning crescent phase, at what time of the day is the moon supposed to be rising? Can we see this moon in the sky? So if it's in a waning phase, as you look at the moon, so the moon is east, or the sun is east of the moon, which means if you want to keep the sun as a reference, so the moon is going to be to your right hand side in the sky. So let's see if that's the case. Let's go to the night sky. What time I put it here? Let's go to 12 o'clock. 12. Today is the 20th, so it's all fine. So if the moon is right of the sun, you could probably show an ecliptic line, and then we can scan the sky to find the moon, but the moon is already gone at this time. Let's take another time. How about 9 a.m.? 9 a.m. Okay, that's better. There you go. So we have the sun in the sky, 9 a.m. In fact, this is almost 10 o'clock, 9 a.m. And let's go back to spy on the moon's phase. Look at this. The moon is waning crescent. So the sun, if you can see my marker, my pointer. The sun should be somewhere here because that is the lead part of the moon. So the sun can't be to the right side of the moon. The sun has to be to the left side of the moon. And that's what waning phases are. And the waning phases, the moon is in the left-hand side of the moon as we look at, or in our left-hand side, if you will. Therefore, if you find the sun in the sky as we do here, right, the moon has to be on the right-hand side of the sun. So scan the sky. And if you scan properly, you might be able to see the moon's right there. See that? Right here. That's the moon. If you allow the Dale or diurnal motion just to operate, so at about noon, that moon's gone. The moon's not in the sky anymore. But every day during this week, at noon, let's go to another day ahead. Since, as we are learning, the moon in respect to the sky, to the stars in the background, kind of a move towards the east, about 12, 13 degrees per day. So every day we expect to see the moon approaching the sun. Look at that. This is for tomorrow, February 21st, and then 22nd. See the moon right here? 23rd, and the moon is getting in a waning crescent phase, and then eventually it's gonna hit the new phase in February 26th. Now, although it seems to be eclipsing, but if we expand it, there you go, too much. See, the moon is not picking up the sun. Where's the sun? There you go. So see, the moon is left of the sun. So technically, in this moment here, the moon is already waxing. This is a waxing phase, right? This is already a waxing phase. And if we allow the time goes by. Oops, that's too fast. So I went too fast here. So if we allow now the time goes by, every minute, every few seconds, every second, they both set in the west sky. And then let me stop here. So if I go now advancing one day at a time, so now the moon is in a waxing phase. See that at 6:28 p.m., February 28th, then the moon is nicely visible. Probably not so nice and visible, but you can see a little tiny crescent of the moon right there. And this is March 1st. Okay, so this is so much for the moon. The moon is going from a waning phase, being west of the sun, to a waxing phase, being east of the sun, in the next few days, and we will not be able to see the moon very well in the sky. Okay, but the sky is showing some interesting things. In fact, it's this one of the most beautiful skies I think I know. So let's go to February 20. So February 20 at 6:30 p.m. If you can go out, Venus is ruling in your western sky. Let me call labels of planets and moon. So Venus is right there. See, is bright in the sky, and if you happen to have a nice pair of binoculars, and if you have a nice pair of binoculars, and if you happen to be curious enough to point at Venus, let me center here and point there. So if you look at Venus with a telescope, this is what you see. Looks like a moon, right? You say, oh, it's the moon. So it's not the moon. It's Venus I see with a telescope. Is in a waning phase. In fact, is approaching in this phase in the sky. Venus is approaching the sun in the sky as we see it, and is going to its waning phase. Okay, let's keep going away. There is a comet there, Encode 2P, magnitude 7.55. You can't see it with the naked eye, right? So you need a telescope and you need to know what it is, and then you can locate it. So Mars is east of Venus. So if you find Venus, if you want to find Mars, is a reddish guy. 8 degrees. 8 degrees is a fist, less than a fist. You make a fist with your hand and place the fist at arm's length. And then you find Mars. Mars is pretty much close to the ecliptic. Uranus, you can't see it. And then if you follow the ecliptic, let me reduce right here. So the sky is quite impressive because Sirius is the brightest star in the sky, and then you can see Sirius quite well. And an asterism, Orion's belt, is sort of aligned in a way that you can follow Orion's belt and then find Sirius quite well, Orion's belt. But if you keep on following from Sirius to Orion's belt, you're gonna hit the face of the bull, Taurus, with its bright Aldebaran, which is the eye of the bull. And if you keep on going, you'll find the beautiful Pleiades. The asterism is also a star cluster, seventh sister. And if you now take the telescope and you center on Pleiades, and you try to view it, then you find a star cluster in there. Okay. So the seventh sister is looks like a little deeper, right? So 1, 2, 3, 4. But with a naked eye, I can only see 6 of these stars. So this is a star cluster about 500 light years away, and has about, in fact, 400 light years away, has about 500 stars, and is in a process of, the stars are pretty much, so this is what you see with a telescope quite well. So we have 1, 2, 3, 4, 5, 6. You don't see the 7th one, but it's called the Seven Sisters, Pleiades. And Taurus, and then if you keep going, Orion's belt. Now Orion's sword is another asterism, and if you look at it with a naked eye, it seems there are 3 stars. But if you look closely, especially if you place a telescope in there, you'll find a very rich region. In fact, the region is a star-forming region. Let's take a close look. There you go. So Orion, this is Orion Nebula. Orion Nebula is a star-forming region, and all this glow comes from OB stars. In fact, the O star and the trapezium. Let's see if I can magnify them here. I think I lost them. Yeah, here the picture is not showing well, but if you look closely oh, there you go. So you see these 4 stars, 1, 2, 3, 4. The brightest of them all is in fact an O star that has a heck of a ultraviolet radiation, and this ultraviolet radiation is creating the glow, the entire glow in the nebula, and that's how we see it. So all this glow is in fact recombination light from hydrogen atoms that have been excited by ultraviolet radiation from this O star. And if we had radio eyes, we could see extended regions here indicating star formation, basically. Now, if you look north, so let's see a star cluster right here. This nice star cluster. I don't know the name of that star cluster, but this is the type of things you can find if you had a telescope. And oh, there's another comet there. Apparent magnitude 5.42. Might be able to see with a telescope if you know where to look at. Comets are chunk of ice with fragments with dust. As they approach the sun, they burn out, and this coma and this tail comes as a result of combining effect of solar radiation and solar wind hitting this comet. So where I am, I was going to look north, but for some reason I lost my background. So let me go back to Starry Night. Oops, sorry, some personal thing here. What happened with Starry Night? Quit Starry Night and start again. Well, I basically was going to look north, but see if I can bring it again. There you go. Oops. Okay, February 20, 2021, that's the time of the day now. So let's take a look at 6. How about 9? 9 p.m. and let's look north. If you look north, the Big Dipper is not easily founded. In fact, if you want to locate Polaris, the star Polaris, right there. I'm sorry, that's Capella. Polaris is right here, I think. Yeah, that's Polaris. So Polaris is easily identified if you know where the Big Dipper is. Here's the Big Dipper. So the Big Dipper has a handle, 1, 2, 3, 4, and a dipper, 1, 2, 3, 4. So you take the 2 stars in the dipper. So that is the configuration of Big Dipper on February 29th, 9 p.m. So you take the 2 stars in the Big Dipper and draw a line, and then you find Polaris right there, right? And if you keep on going, there is another asterism called the W or Cassiopeia. It's right there. Now, if you locate Polaris, oops, just draw a line straight down, perpendicular to your horizon, and then you're gonna be very much close to north, to due north. Okay. Less than 1 degree, so it's right there. There's no missing. And how many degrees there is? About 37 degrees, right? Going to from Polaris straight down. So Polaris is part of the Little Dipper, and so you have 1, 2, 3, 4, and another 1, 2, 3 is right there. That's part of the Little Dipper. And so this comet, if you want to try to find it, parent magnitude 5.44, and this is a 9/11. So take it's is between north and northeast. You're due east, and at that time 9/12 is this comet is, oops, oh man, stay there. There you go. This comet is about 3/5, 30 degrees from your horizon, and from the second star, about 30 degrees from the second star in the handle. By the way, the second star in the handle is interesting because if you look in the telescope, it's not a single star. In fact, it's a group of 4 stars. Look at that. Just the glare go away. It's not going away. I thought it would go away by now. But there are 4 stars in there. In fact, in some traditions, one of the stars in this group were part of the 7 sisters. And that's why you can only see 6 of them in the Pleiades cluster. It's just a myth. All right, so more for the stars later. Don't know why it's getting fuzzy. It shouldn't be fuzzy. Oh, there you go. It went away. See if I can see now better. There you go. And there you go. So we have 2 of them star. I mean, when in a naked eye, you can see this and that one. And this one, you barely can see. In the Roman Empire, if a soldier could see that, would be higher. It means you can see your enemy very far away. But with a telescope, you can resolve 2 here, 1 and a third and a fourth one there. So Mizar. This is the second star in the handle of Big Dipper. And then, so 30 degrees about 30 degrees towards east, you'll find a comet. Now I can't move it. And again, you gotta have a telescope, or it's not gonna be easy. Yeah, about 30 degrees, 3/5, and then another 3/5 straight down. So scan the sky, see if you can locate it. It might be not so challenging. Okay. Now, for the Astro News, the article is about determination of. I'm not going to say what it's about, but my seed, the seed, what I would like you to, in fact, is about something, and you have when you write your explanation, which is the second part of your report, you have to determine what sort of instruments were used to do what they did. That's very important. And I want a name of telescopes. If there is one telescope, the name of one telescope. If there is an array of telescopes, you give an array of telescopes. If it is space, just give it the space telescope. So that's important because, as we have been discussing here, astronomy is science, and it's not a speculation or theory or something that is not proved. In science, theories are based or are created and developed to convey data, to pretty much incorporate and explain um, the onset of data. And also, good theories predict things that we don't know. That's the beauty of theories, the beauty of science. It's not a speculation. For instance, in mythology, in religion, in probably in social science, maybe no, social sciences follow the scientific methods. But in religions, in mythology, in arts, you have the freedom to do whatever you want, to say whatever you want, and no um, there is not an agreement or a compromise with accuracy and with measurement, with data, right? So you can say basically anything. Um, for instance, I could say if I believe in a religion, if I'm a part of a religion that believes and dictates the universe was created by, let's say, the burp of earthworm. That's a crazy theory. But let's say that I'm a member of a religion that believes on that, right? So, and I could create a theory to explain that. Well, earthworms, they eat a lot of junk things, um, and because their stomach has to process that, sometimes they create gas and they burp a lot. So then the universe had a big earthworm, and that earthworm burped and created everything. So it's a theory in the views of a religious person. In science, this is not a theory because it's not based on any evidence that exists some almighty being that looks like an earthworm that can create things, because I cannot summon that being to my laboratory, and I have any way to quantify it, to measure it, to do all of the things that science does. Now, when we talk about scientific theory, it's different. We measure things, we quantify things, and and once we accumulate data, we try to explain how nature does stuff in order to create and to produce that material, that data, and and then we create a theory that is based on pre-existing knowledge that has been confirmed, by the way, um, and and then we use the theory to explain why things are the way they are. A good theory can even predict things we don't know, right? But it's not something crazy. It's something that has some basis, and its base is the evidence is always nature, is always an open book. That's why you can say that science is a natural science is it's something that attempts to explain how nature works, and it has to be based on evidence, basically factual, if you will. So so which means in astronomy, as being a science, the instrument we have are telescopes and detectors. So why is that? Well, because the objects we studied in astronomy, they are so far away, we don't bring materials from them to the laboratory because they are too far away. We haven't been there. So how can we say how hot they are, what sort of a chemical composition they have, what rotational rate they have, how old they are, how they were formed, and what sort of a population they are parts of. So how do we do that? Well, because light and interaction of light with matter, we know well. We does experiments with light and the processes that leads to absorption and scattering and emission of light from materials. So because we know that, we can say, hey, we should build instruments, telescopes, that can collect light from faraway objects. And since we know the resulting interaction of light with matter, see if we collect light from these faraway objects, we can then um, estimate what they are made of and what sort of a chemical or physical processes are going on in their atmosphere to produce the light we observe. And therefore, you don't need to go there because light is information is already going towards you, observer. And what you need to have is telescope. So telescope is an important instrument, and every single scientific papers in astronomy describe what sort of an instrument was used to collect information or light. So here's the seed you need to know. I want you to explain what gravitational lenses are. I mean, the whole point of this article is based on gravitational lens. So what are gravitational lenses? Now, if you go to our book, let me show you where. So you go to OpenStax. OpenStax. And I know you're going to say, oh, OpenStax, you are talking about material that is going to be given all the way to the end of the semester. Well, yes, and it's not. I mean, it's astronomy is just one thing, and so we go all the way to not here, no here, no here, no here, no, nope, 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 no black hole. Black hole's cool, but it's not. This is what I want to talk about, and probably look at evolution and distribution of galaxies. Evolution and distribution, observations of distance. So try this chapter here, okay? And you might also get a nice information of what gravitational lenses are. And so that's the seed, what gravitational lenses are, and why gravitational lenses are being used in this particular article to find out what they want to find out. What gravitational lenses do, basically. Okay. Now, in the article, if you read, there is an animation that explains how gravitational lenses work. So take a look there and talk to me if you're not certain of what's going on. Okay, bye.